This is part 3 of my talk, using mathematics to help cure hunger, disease and global warming, an analysis of solar concentrators. In part 1 we looked at and part 2 we looked at a simple solar concentrator consisting of a box with a reflective lid. We're now going to look at parabolic reflectors. And we're going to introduce a new ratio. This is the F number. The F number on a parabola, a parabolic reflector, is the ratio of the focal length, the distance between the vertex and focus of the parabola, divided by the diameter of the mirror. So you see parabolic reflectors with various different kinds of F numbers. Here are some with a high F number. Here are some with medium F numbers. And here are a couple with low F numbers. And my question is this: which F number needs repositioned least often? The thing, as we discussed in part 1 with a parabolic reflector, is that when it's pointed directly at the sun, all the light is focused on, all the light comes into the focus. When the sun moves on and the parabolic reflector is no longer pointed directly at the sun, you start to lose some of the reflected light. And the question is, does the F number, or to what extent, or how does the F number impact how frequently the mirror needs repositioned? So we're going to model that in geometry expressions. So let me have my axes here, and I'm going to create a parabola. And I'm going to have a couple of parallel lines down here. Let me make them thin and dotted, as these are just construction lines. So these, if the diameter of our mirror is d, then the distance from the axis to these lines, which mark the edge of the mirror, is going to be d over 2. And I'll put points there that they mark the edge of the mirror. If we'd like, we can put an arc in between these points. Let's make that nice and thick. Well, actually, we could just make what we could do instead is make the parabola nice and thin. So this thick dark line here is the actual mirror. The thin line is the parabola, the parabolic shape that it's based on. Now we're going to have we also have a target. Let's model the target, the cooking pot, as a circle. So we can give it a size, that size r. Now, if we have incoming light, here's a ray of light. Let's again change its color from black to kind of orange. So now we need to reflect the light in the parabola. Well, we can't reflect in a curve in geometry expressions, but we can reflect on a line, so we need to create the tangent line to the parabola. no, that's not what I did. Let me do that again. Select the point and the parabola and construct the tangent. There we go. Again, let's make that a little bit thinner. And let's now reflect the ray of light in the tangent. We can see that as the angle between the ray of the light, if the ray of light is coming in vertically, we see it goes right through the focus. As the angle grows in either direction, we gradually start missing the target. In fact, what we're interested in is, can we find the angle at which we just start missing the target? That's the angle at which we start spilling some of the sunlight that we could otherwise have. Again, we're going to use the trick of, so in other words, we would like the reflected ray to go through, to be tangent to this circle. So let's put that constraint in. Now it's not prepared to do that, as well as keeping all the other constraints, so we're going to relax one or other of the other constraints. In fact, let's not do that at all. What I'm going to do is draw the model the opposite way round. So let's start with the reflected ray. Here it is, and let's make it tangent. Change its color again. And again, reflect that back in the tangent. So here we have the critical reflected ray for this location, and we can ask, what is the angle? One thing we haven't done, we haven't actually parameterized our parabola. Let me do that. So notice, as we can put the focus anywhere we like, but we said the important parameter is the f number. So the f number, if you remember, is the focal length divided by the diameter. So capital F is the focal length here divided by the diameter. So in other words, this distance here is going to be f number times the diameter, right? Because then if we take that and divide by the diameter, we get this capital F. And so we see the picture that we have here. What is the f number? It's about, we look down at our variables panel, we can see the f number here is about 0.39. If we wanted, let's say, an f number of 0.5, what would that look like? It would look like that. So what I'd like to do is have a look at this critical angle as a function of our f number. Let's make sure we're in radians. This is going to be a calculus problem. We should be in radians. So here we have it. It's a particular arctangent. We've got an r in there, and we've got the f living on the top and on the bottom of the expression. We also have the f inside an absolute value. I'd like not to have that, so I'm going to change the output properties and use assumptions. So notice it's got rid of the absolute value, and it's just assuming that f is bigger than 0. Well, that's a reasonable assumption. If it is bigger than 0. So I'm now going to copy that. I'm going to copy it into Maple. I could, but let's use TI Inspire this time, just for variety. Let's copy it as TI Inspire. I don't have TI Inspire running, so I better start it. So here I have that expression. Note the Inspire simplified it considerably. What I'd like to do is differentiate that. So let's do that. Derivative with respect to, and the thing, notice Inspire has changed my f from capital to small. It's going to cause me a bit of a problem in a minute when I copy it back. However, let's not worry too much about that right now. I'm going to differentiate this with respect to f. And I get this. Now I'd like to find a solution where that expression equals 0 for f. Well, we can solve that by inspection. We don't need to use the algebra system. Because look, on the top line there, we have this term 16f squared minus 1. What would make that 0? Well, that would mean f squared was 1/16, or f equals a quarter. So we have this nice little solution that f should, for an optimum, f should be, the focal ratio should be a quarter. And notice that's independent of what r is. So if instead of f, we just type in a quarter, we get the optimal solution. Up here we have the angle at that optimum. But notice, if I draw a straight line between D and C, there's something very geometric about this location where f is a quarter. In fact, it's the location where the focus lies in a straight line between the edges of the mirror. Now when we get something, we go through all that calculus and get something as simple as this, we have a tendency to ask ourselves, or I have a tendency to ask myself, was there a way we could have got this answer without going into all that calculus? Could we have answered it geometrically? And actually, one look at our drawing shows that we could have done. Notice that this line and this line, when reflected, give us this line and this line. So if I were to draw a second tangent and then reflect that back in the tangent to the parabola, what can we see? Well, we can see that this angle here, let me just put a real value in there, this angle here is the apparent size of the target when viewed, the viewing location at the edge of the mirror. And that angle is identical, because it's just the reflected version of this angle here. Now we can see that, we can just ask for that angle. And we'll see, indeed they are identical angles. Now, if we're allowed to put the target anywhere on the center line, where is it going to look the biggest when viewed from C? Well, it's going to look the biggest when it's closest, and it's going to be closest when it's a straight line between the edges of the mirror. So we could have had that rather sophisticated geometric argument to solve our problem without going into the calculus. The calculus, however, was quite straightforward, particularly when we're using an algebra system to do the actual symbolic manipulation. So to the answer to our problem, which f number needs repositioned least often, the winner is medium. This one, you can see the focus is right in line with the edges of the mirror.